Mr. Akilur Rahman. He is the Chief Technology Officer with Hitachi Energy, leading the technology giant's core technologies and digitalization strategy and execution for its power giants for power grids business in the region. Today, Mr. Akilur will talk upon energy and digital transformations for power plant performance.
So the time we have very less time, I'll take you through a few examples, but also start with a very larger context for the power plants in the power and energy ecosystem, so that we can ready the power plants, whether they're the brownfield, the old power plants or the new ones, to be enabled for the new energy ecosystem. So starting with looking at very fast forward 2050, I think it's as you know that with COP26 and several utilities, industries, countries, they have announced for carbon neutral vision. And so here it's the facts are that the electrification is going to be be more than 50% of total energy demand by 2050, and a lot of areas which are not yet electrified, especially in the process areas. We are seeing that other areas already done, but process areas and all, they will be also electrified. One example is the green hydrogen, green ammonia, how you use the electrical energy to produce them and also store them for as electricity. So as we know already, our speakers, they have talked about there is a shift from the fossil fuel to the renewable. Here again, we people always think that it's sort of upright or outright replacement of it. It's not going to be replacement, but it is going to be actually transition, and we will still have the conventional power, the energy there, because that also provides us the inertia in the system for the power system to be stable. Whereas the renewables, they are intermittent, and also it's going to be a sort of hybrid system in future, and then see how we can transition towards that. And that's the reason why you see 2050, 2070, like India, we have the target. So what's required here is in terms of how we transition from the pure conventional or majority conventional to the hybrid system, where it will be conventional energy, the thermal energy, and other forms of conventional energy, plus the new energy, the renewable energy. Then also use the digitalization to make the transfer faster, and also ensure that we can still make the grid stable while we move towards that. The future, so this is just to give a very larger context of how the power plants in the future power systems, they will be. From the generation, we have seen the traditional generation, the wind of course has been there, but it will be more and more. Pumped hydro, they have been there for several years, but it is going to be more and more, because we need the storage of energy, because the wind and sun being intermittent. So then I talked about the hydrogen, green hydrogen, how we can produce that, use that in the process industry, as well as use that for the hydrogen fuel cell based storage. And so with that, the grid also needs very strong control of these different, as I said, the biggest advantage of our conventional thermal power plant was that they were providing us the inertia in the system, so grid was stable. But in future, it is going to be a bit challenging. That's why mix of different technology sources, and we have to bring in also more of power electronics based control. On the other hand, we'll also have a lot of electric vehicles, power quality topics which have, so that way we will have new areas like meshed HVDC. We'll have also a lot of static compensation of power for the power quality, for the power factor. So the power plants, they have to be ready to adapt to this kind of new ecosystem, new system of generation, transmission, and distribution. And also the power plants will also be more and more distributed, smaller ones, distributed, conventional, as well as new renewable energy. So that's how the transformation is going to happen. And coming to the digitalization, how we can leverage it. So this is one example of how the power equipment in power plants can be digitalized, because we know that in power system, in power plants, we already have the distributed control systems, automation with all the sensor there to manage, to control it in real time. So very, very sophisticated, very advanced level of applications we have, more than what IT world says today. Automation, digitalization, I think power plant has been there for several decades, so we should be proud of that. So here what we can do is we can extend these sensors, the systems, to capture the real-time data in the cloud automatically, and then this data is available for larger set of experts within the power plant, outside the power plant, outside in the other service providers, and also in the transmission utility, so that they can also analyze the power plant assets, operations, systems, to provide advisories, to provide suggestion, expert advice how to improve the performance of the power plant. So here again, so here when we talk about digitalization, so there are several technologies we know. I mean, I'm not going into the details, but I'll show you some examples, whether it is the digital twin, the model, the simulation model of the power plant assets, or it is virtual reality, augmented reality, cloud computing. So all these technologies are there. AI, ML also, forecasting of energy production when it comes to the renewable energy. At the same time, the load pattern, the demand, that also is there. But very important here is that we need to define the KPIs in terms of what performance parameters in the power plant we would like to improve. Its productivity or reliability, quality of power, and quality of the raw material in the power plant, and also the assets, the very important assets we have in the power plant, like one generator and one turbine failing or malfunctioning can create a big impact in the system, and which also goes to the consumer, whether it's industrial or residential or infrastructure. Energy efficiency, of course, we are talking about safety of people, environment. How do you monitor the pollution, the environment, the gases, the air in the power plant and surrounding area. And of course, cyber security is very important, because we have more and more automation and digitalization in place. So this is the system, what it says. On the left side, we have the conventional power plant with conventional assets and systems and operation, but we are extending it with the IoT and digitalization, with the sensors, and then achieving this higher level of performance. So this is not actually replacing our conventional system or assets and operation. This is only on top of it. So many times, people say that, okay, digitalization, automation is going to replace the conventional. It's not that. I think the power plant, as I said, they are already, advanced level of algorithm, time-tested algorithms, applications they are running. So that we have to protect, we have to secure, and then we improve the system further with this additional technology. One example is this asset management, where we put the additional sensors. This is an example of course, transformer, but similar to a turbine or generator or any plants, the utilities in the power plant. So we take the data, offline data of the asset, data from the control systems or SCADA, and then the online sensors. We put additional sensors, and then we have the model for that particular critical asset there, which can provide a platform where we can run some application algorithms, which will give us indication about the asset's health, whether it is going to fail in few weeks, or it has already failed, or it is in perfect condition. So this is an asset health index which can be provided, and here AI ML applications can run to predict any malfunction or failure of the equipment, whether it's a transformer or generator or turbine or any plant, also in the subsystem level as well as the entire. So this will help also to ensure that the downtime in the power plants we can reduce. So we can also prevent any surprise failures, malfunction, because that, as I said, power plant, they are very key. One transformer, one generator or turbine failing or malfunctioning can actually create a big impact in the system. But I think the base is there already in power plants. We need to just adapt the new technologies, sensors, and the asset management process. So this is example of how the transformer is, for example, digitalized. Similarly, other equipment in the power plant, generator, turbine, and all, they with the sensors, and also a lot of sensors, the instruments in the power plant, including the electrical equipment, they are also now becoming electronically enabled, in the sense communication enabled. So that's also very important to get the real-time information about the assets, so that we can do the predictive analytics, we can do asset management, in addition to the control system, which is a closed-loop control system in power plants. So this gives us the opportunity to have all the assets in the power plant, the fleet of assets, and then see which are the assets in the red condition, they are already failed or maybe about to fail, and in the orange yellow state where they might malfunction or fail in few weeks or months, so that you can accordingly take them for maintenance, instead of having a surprise tripping of any equipment in the system. So this also gives you very detailed, you can deep dive. So this is all asset management dashboards where you get the information from the sensor automatically, and then the application is running. There is also the expert base available, where you can capture all the experience of the operators, the maintenance staff earlier who have worked on this and solved the problem. So that is also there, in addition to the automatic the asset management algorithm, but also you have the expert, human expert. Another example is how we can use the robotic technology. So this is of course from Hitachi Energy. We have this robot which we have developed, which can go inside the transformer, big power transformer, for example. It can go inside the transformer, and it's called diver robot. It can do the inspection. Otherwise, as you know, the big transformers, you have to do the inspection, then it takes almost 2 to 3 weeks time to take out the oil, take out the other components, and then you send human being inside the transformer tank to do the inspection. But in this case, you don't have to do that. You don't have to take out the oil, but the robot goes inside and then dives and then does the inspection. So that way we can reduce the downtime of the transformer from 2 to 3 weeks to only maybe 1 or 2 days and do the inspections, and then the transformer can be back in the system if it is healthy, or you can do some maintenance. So overall you reduce the cost. Overall you also reduce the downtime of the transformer. So these are the technologies. So this is again another one where it's wirelessly controlled. It is also connected to the cloud, so that the remote experts sitting elsewhere in your other plants, or maybe with your OEMs, they can also look at the inspection data, analyze it, and then suggest some measures to correct or maintain it, repair it. So going a bit more beyond the asset management, you also have this connected to your grid, with the load, with the generation, with the market data, weather data, so that you can also have holistic information about this asset, how it is going to operate, and also how the maintenance order can be generated automatically, how the crew can also go to the exact location of the asset to fix it. So this is the digitalization asset management, which provides us an opportunity to do digital twin. So you have the model of the power plant, whether it's a turbine, generator, or transformer. So you create that, and you can use this digital twin to actually compare the performance of the equipment in real time. Sensor, data coming from the sensors, you compare it with the design value, and then see whether there is some trend which is sort of going away from the design value. So you can take action. So this is again, is possible with the digital twin, the model, which can be also run in real time along with the asset management system. The entire installation of power plant. So for example, here in Hitachi Energy, we have come up with the world's first digital twin for installation, large electrical installation. So for example, here it's for PACTS installation, flexible AC transmission, electrical installation, high voltage, extra high voltage. So here you, even without going into the physically into the installation, the substation or system, you can also sitting in the office, you can walk through the installation, you can learn about the technology, you can also see the real-time data. So this is again possible, by which you can actually get trained, you can find some issues, problems in the power plant which you can work on to improve it. So that is how. So these are the tools to help you to improve the performance. And so this whether it's digital twin or any kind of application, we need to do it based on the life cycle approach. You plan this, create the model, you build and operate and maintain. So life cycle, if it's a brownfield, you can start with wherever you are today, create the model, the 3D, the 4D model, and also the profile, the thermal profile, the electric mechanical profile of the equipment, and then work on the digital twin to find any issues in the asset and then improve it. So with all these, automation, software, digitalization, so there is always worry that, okay, what will happen to the cyber security? What will happen to the system in case of cyber attack? So I think this here also we have solutions in terms of how we can protect the installation, whether it's a power plant or it's a power evacuation system, the substation, the automation system where we can have the detection of any issue, or we can also have the protection in terms of malware protection, or maybe how to create a sort of defense in depth kind of security layer in this system, by which you can protect the system. So also in terms of IoT, if it is the data is additionally in the cloud, whether it's a public or private cloud, you can also have mechanism to detect and secure the communication, secure the data. And so finally saying that, so all the technologies are there for improving the power plants performance. So here we have to ensure that first we start with, I'll just show the pointer quickly. Yeah. So start with defining the key performance parameters of the power plant in terms of productivity, energy, quality. So what are they? And then do some kind of assessment that where are you in terms of the power plant, your own power plant operation. So this is the assessment which is done. And once you come up with the reference point, then you can identify some solution in terms of what further automation you can do, what sensors you can put, what applications you can run, predictive, prescriptive maintenance applications, and then you install, you monitor, and then again you do assessment. So it's not that in one go you can do everything. You can implement all the solutions, but you can do it on a continuous basis. I think this is one area where we know that the power plants we have in the country, there are many power plants, they are running for several decades. They are good. I mean, they are still running reliably, but we can still have more efficiency from them. We can also have more predictability because they are aged now, but we can still predict any malfunction, failure in that. So with this, I think we will be able to address the energy transformation which is happening towards more and more renewable. But with the power plants, with the conventional one, how they can also coexist in the system, and also digitally, how they can be enabled for more efficient operation of that. So with that, I will just stop here. Yeah.
Thank you, Mr. Akilur.